Hi, I'm Kush Patel, and this is my lab report on projectile motion. So the purpose of this experiment was to compare the projectile motion of a real object to a computational model that includes drag and one that excludes drag. So for this, the main physics principles that are at play are Newton's second law, the velocity update formula, and the position update formula, which we use to help track our object in the models and also to understand where they are. The forces at play for this are the force of gravity as shown, the force of drag which is calculated as shown. Now we know that the net force on our system is just simply both of those combined, as those are the only forces we're accounting when we're predicting the motion. So for this experiment, we threw a marker cap onto the table from a set height. The system in this experiment would be the marker cap, and the surroundings would be the table and the air. For our tracker data, our initial conditions were the position as shown, along with the velocity as shown, which we calculated using the first two frames of the tracker app. Here are the main key points of our code. I'll briefly go over each part. So over here we have the initial conditions, which were just taken straight from the tracker app and the values that it had for the initial position and the velocity. Well, the velocity was actually calculated using the first two frames. We found the initial velocity. The time started at time t because we had adjusted the video to where it starts the moment the marker cap leaves my hand. And then the delta t is 0.033 seconds because that's the time it takes for the tracker app between each frame when we are plotting the points. We have to include g equals 9.8 so that way I can recall that later in the function. Rather than just plugging in 9.8, I can use g as a variable. This first part of our FNet equation is the force from the gravity, and that's more simpler to see than this second part, which is quite long and quite an extensive way of showing the calculations for the drag. Again, these are values taken straight from those formula, or this is just directly the formulas that were shown before, except it's a little expanded just to use the values that we had in tracker and not to have to do any extra calculating on the side. And I've condensed it all into one FNet formula rather than breaking it up and then adding it together. And then we also have our velocity update and position update so that way we can track it in Tractor and get points for graphing as to compare the models. Here's our data from this lab. As you can see, we have the the two models and then our actual data in different colors. Red is the actual, blue is the model with drag, and green is the model with no drag. Some important notes are that since the drag coefficient is quite small, the model with no drag also follows a pretty similar line as our actual data. And that drag coefficient was simply found by plugging and playing until we found a model that accurately showed something similar to our actual data. The first possible source of error could have been choosing the incorrect starting frame from the tracker, only because there could have been a frame where the tracker was, or where the object was still accelerating from the hand, or a frame where after it was released from the hand, giving us the wrong initial velocity. And also it could be choosing the b value because our b value was guess and check. That's how we found it, rather than finding a specific b value that is specific to the marker cap. Additionally, the marker cap has an inconsistent shape, so there's no telling exactly if it's flying perfectly, as you'd see in a model. So one question is, do either of the models predict the terminal velocity? Short answer is no. If we look down, we can see that these two graphs, they show the velocity versus time of our model with no drag and the model with drag. Now, terminal velocity is the maximum velocity an object will reach before it hits the ground. So we can't see a point where in the velocity where it levels out and is flat. Our velocity is constantly changing. It has a slope. A point where the slope would be 0 is where we can indicate the terminal velocity. So yeah, like it says, if the drag was greater or the object fell for a longer time, we could more easily see this. Now, by taking our model with considering the drag, and we were to extend the time period of the way it tracked, or if we were just to make it fall or create that drag even stronger, we would see a trend that follows a more curve like this to show that the velocity is leveling out into a constant. Another question is, what if the object was thrown straight up? Would it take the same time to reach the table? And it would not. The time it'd take would actually be longer because not only would the object be accelerating up as opposed to ours accelerate out, it would also have to accelerate back down from the position it reaches. So gravity would be doing work as it accelerates up and also having to do work as it accelerates down, causing it to take a little more time to get down to the bottom or reach the table.